Hey there, everybody. Mr. Newland here. Let's talk about rotational collisions. What happens when a rotating object has a non-rotating object, say, dropped on it? So, yesterday we mentioned that the change in angular momentum as a function of time is the net torque. I would also remind you that this could be the derivative of momentum with respect to angular momentum with respect to time. Angular momentum is defined as I times omega, or you could write it as R cross P, which is the same as MVR sine of theta. Kind of fit that in there at the end. So what happens if I have, say, a disk? Let me see if I can get the software to draw me a disk. Good. That's moving with some angular speed omega. That's supposed to be angular. And it has some known rotational inertia I. Let's call that actually I1. Because what we're going to do is drop, let's make a purple one here. And in fact, let's use the little dash lines that one of y'all showed me how to do. Try to draw a circle with dash lines. Yay. And it's not going to be perfect, but they have a common rotational axis. So maybe we should indicate where that is. So they've got a common rotational axis. They each have different radii. So we'll make this guy capital R1 and this lowercase one capital R2, and it has rotational inertia I2. So what's going on here, y'all, is that the larger disk with the bigger radii, with R1, was already rotating with the speed omega. It was going in a counterclockwise way. And then we're going to drop a non-rotating object with radius R2 on top of it, the one that's the dashed line. So the deal is, if there's no external torque in the system, if all the torque is happening just because the dash line circle wasn't moving, there'll be friction between the dash line circle and the bigger circle. That friction is going to cause an internal torque. But if there's no external torque, then we're saying that the initial angular momentum, which is just from the rotating object that was already spinning, will have to be equal to the initial angular momentum, will have to be equal to the final. So when we started, the only thing that was rotating was the larger disk, which had speed omega, and let's call it, omega. Let's actually call that omega naught, y'all. So we'll call the rotational inertia of the spinning larger disk, the one with radius R1, we'll call that I1, and it was moving with an initial speed omega naught. And then after you drop the smaller disk on the larger one, there'll be a new rotational inertia for that system. It's the sum of the two. So I1, the larger disk, plus I2, the smaller disk, they have the same rotational inertia. Now, this only works once they have both achieved the same final speed. So if you drop that purple dash line disk onto the larger the R1 disk, there'll be some friction that will cause some torque, which will use up some of the rotational energy. And eventually, this new system with two disks, one piled on top of the other, they'll reach a new, slower speed. So the idea is, yes, there is a torque, but it's internal. Yes, there's an energy loss, but it's work done internally. The angular momentum is conserved between when you before you drop the thing and after you drop the thing. So once the friction stops acting from the smaller purple disk onto the bigger disk, once that friction stops and the torque stops, they'll reach some new angular speed. But the idea is that their angular momentum never actually decreased, so it has to be the same value. So assuming you can calculate, don't forget, by the way, for a disk, I1 would be nothing more than 1/2 M1 R1 squared, and the rotational inertia for the second disk, because all disks have the same rotational inertia, 1/2 mv squared, M2 R2 squared, like that. And now all we are trying to figure out is what's the final speed of the two disks. So in a pivot lab, very similar to this, the students are asked to measure omega naught by taking delta theta naught over delta t naught, like that. Literally change in position over change in time. The rotational inertia can be calculated from the formula. In the idea of angular momentum, this net rotational inertia can be calculated by literally adding the two together. So what we're saying here is the final speed of this system is going to be the I1 omega naught over the sum of the two rotational inertias, like that. And so you can actually figure out the final speed of the system without having to measure anything else. And it's very similar to like when we've done, what's that thing called? A ballistic pendulum, where we had to use momentum to figure out the relationship between the initial launch speed and how high it climbed. This is kind of in that same sort of wheelhouse. We're saying that the final speed of this two-disc system is going to be completely dependent on the initial angular momentum and the rotational inertias. So you can figure out, and this is also like we've done with other linear momentum scenarios where the initial momentum was equal to the final momentum when we figured out the speed of the system. Oh, I would also point out that this is in a linear momentum sense, we would call this a completely inelastic collision. For rotational collisions, you should assume that they're going to be completely inelastic. That's usually, at least for College Board, what they ask. They're asking, what's the final speed of this new system when they one falls on top of the other. So hopefully that will get you going on any problems related to rotational collisions and if you have to do a pivot lab. All right, y'all, that should work. Bye.